Good morning, everyone, and thank you for joining our second webinar on the hydrogen topic. I see that the first participants are already here. We will be starting on time as planned in a couple of minutes, and I would like to give you a brain teaser as introduction. Try to guess what would be the timeline of the first high-speed train fueled with hydrogen. I will be providing an answer to that question at the beginning of our webinar. Thank you. I can see that more participants are joining. We will be discussing the timeline of first hydrogen-fueled high-speed trains in the coming years. Please provide your guesses in the chat tab that appears on the right side of your screen. Once again, thank you for the ones who joined in time. We'll be starting in a minute. Great, more people are coming in. We start in 30 seconds. Please do not hesitate to post your answers in the chat tab on the right side of your screen. Well, it's 11 a.m. Paris time. We will start on time as I mentioned before. Thank you once again, everyone, for joining our second episode of Hydrogen Webinars. Today, we will be talking about the application in trains. I will introduce myself pretty quickly before moving on to the agenda of this webinar, and then I will start by providing an answer to the question I asked a couple of minutes before. I'm Armin.morabbi, manager at IAC Partners. I have been working on different hydrogen topics for the past couple of years, and I will have the pleasure of presenting this webinar to you. This presentation will be moderated by my colleague Olivier Saint-Esprit, who's an associate director and partner of our company. Today we will talk about the following topics. I will provide you with a brief introduction of the hydrogen market and ecosystem. Then we will have an overview of low carbon solutions for the railway industry. Then we will have a look at more detailed segments of the rail transport market. We will be comparing both the cost impact and CO2 emissions of these technologies, and we will finish by discussing the challenges of the large-scale deployment of hydrogen trains. And we will keep 10 to 15 minutes at the end of the presentations to discuss potential questions, and I will be trying to answer those. Once again, during my presentation, if you have any questions or remarks that you want to discuss, please do not hesitate to write them in the chat. My colleagues will transfer them to me, and I will make short stops discussing what needs to be clarified. So without further ado, I would suggest that we begin. I will begin with the question that I asked just before we started regarding the hydrogen high-speed trains. Well, it will most probably never happen. There is a technical challenge regarding high-speed train, which revolves around the volume of hydrogen that we need on board to fulfill a pretty typical high-speed train trip of 800 kilometers. For our French audience, the Paris-Marseille line is the one who speaks to them pretty well. In order to do that, you need 50 cubic meters of hydrogen on board, and that volume of hydrogen will be at 350 bars. And in order to store the hydrogen tanks on the train, you will need to dedicate two out of the 8 coaches that we currently have in France in a high-speed train to the storage of hydrogen. And I'm even excluding the fuel cells and the small batteries that you need to embark on the rolling stock as well. So it's technically not impossible, but financially hardly viable if we remove 25% of carry capacity that we have on board. But there are other potential applications for hydrogen in the railway industry. We will go into more detail on those, and we will see where it would make sense to move to hydrogen technology. Before discussing the railway specificities, I just want to start with a brief overview of the hydrogen ecosystem. Hydrogen is currently considered for 4 different applications across the world. The one on the left as a raw material for industry has been the case for at least a century or even more. In this application, hydrogen is not used as an energy source per se. It's considered as a raw material, especially for chemical transformation and the production of chemical products such as in refinery in the petrochemical industry, or in methanol or ammonia production. And there is actually one process of steel making which consumes a few millions of tons of hydrogen per year, which is the direct iron ore reduction as well. So these are the main historical applications, which represent more than 96–97% of current global hydrogen production. But there are three new applications which are coming in, one of which is of more interest to us, and I will keep it for the end. The first one is hydrogen as a means of storing renewable intermittent energies to be able to use them when needed. So it's all about balancing supply and demand of electricity on the grid. So once again, in competition with batteries or other means of storing electricity. The second topic is decarbonizing the heating. It could be in residential, industrial, or tertiary applications. The idea is pretty simple. If you introduce a certain percentage of hydrogen in the current existing urban gas networks, you can burn a mix of natural gas and hydrogen, which will lower carbon emissions in the heating application. And last but not least, and that's the topic that you have most probably heard the most about, is the use of hydrogen as a replacement for fossil fuels in different mobility applications. There are a lot of progress. There is a lot of progress being done in different applications. It all ranges from low-duty vehicles fueled by hydrogen, going all up to large vessels and even aircraft, as I'm sure our French audience is at least fully aware of the initiative launched in France. The maturity level is obviously different, and there is one particular application about which we will be talking today, which is the railway industry. But before moving to the pilot projects in the railway, I would like to make a statement about all the fuss about hydrogen. There are people believing that it's one of the new hot topics and it will be forgotten in a couple of years, as it happened, but with several different topics in the past. But this time it seems to be different, especially if we look at the amount of money which is being committed to the development of hydrogen strategies in different areas of the world. well, this slide already summarizes somewhere around $200 billion being committed, the largest chunk being in the European Union at around 150 billion. And there are two major topics that you already do not see on this slide, on which announcements are expected quite imminently. Two of the largest economies in the world, the United States of America and China, are starting to announce their ambitions in terms of hydrogen ecosystem. To give you a large figure, if you had time to look into Joe Biden's program, he will be committing somewhere around $1.7 trillion over the next 10 years in climate-related topics, the exact share of which will go to hydrogen is still to be completely finalized, but chances are there's a big chunk of it going to hydrogen. And one precise ambition has been announced, at least in the program of Joe Biden, which is the production of hydrogen at a similar cost level compared to the shale gas, which will be pretty low, and which is a pretty ambitious target. And the second topic is the 14th five-year plan of the Chinese government. We know that the major guidelines in there, but the precise figures are expected in the coming weeks. The Communist Party meeting took place at the end of October, so it's only normal that we get the details in the coming weeks. So it will be happening, especially if we look at the pilot projects and the amount of money which is being dedicated in that. Three major regions are concerned by the deployment of hydrogen at the beginning. Mainly Europe, North America, and Southeast Asia are the pioneers on this topic. And there's even stuff happening in the railway industry. For the ones who are familiar with the railway industry, I'm sure you have already heard about the Coradia Island, which is the world's first hydrogen train, which has been running for a little bit more than 2 years now in Germany. Newer ones have been running in Austria, the Netherlands, since a few months already. And there are programs announced in Italy as well, with an order of 41 train, if memory serves me right, which will be coming in the next 5 years in Italy as well. But Alstom is not the only one developing hydrogen trains. The two other European train manufacturers, Siemens and Stadler, are already developing hydrogen fuel cell trains as well. We have a tramway already running in China as well. And even battery trains are being developed already all across the world. Before moving to the segmentation of the railway industry, I would like to speak a little bit technically about the different traction architectures that we can have on the railway industry. Well, the historical application, the historical architecture was about the diesel trains with the simple architecture, a diesel tank, diesel going to a combustion engine, providing motion. And the train will move. The second technology, which was introduced in order to reduce carbon emissions already, which was the electrified lines, providing electricity through a pantograph to the train, so no energy stored on board, going through a transformer before feeding the electrical motor. And then, due to infrastructure constraints, we developed, especially in Europe, the hybrid trains, diesel electrical hybrid trains, where a part of the line was electrified, on which we actually had the electrical train architecture. And on the parts of the line which were not electrified, a smaller diesel tank was on board. It fed the combustion engine, which in turn, through an alternator, was able to provide the energy for the electrical motor. And two new technologies are appearing as well. As I mentioned, trains with batteries on board, which are pretty similar to the electrical trains, except that you remove all the electrification infrastructure and you store the energy on board inside a battery. Well, the difference being that the energy stored on board is in direct current form, so you need an inverter on board as well to feed the electrical motor. Or the most recent technology and the one which is of most interest to us today, which is the hydrogen train. And I think it's important to take a minute or two to discuss how it works in order to understand what are the main challenges of a hydrogen train. Well, you need to store your energy in form of gaseous or liquid hydrogen on board. Then this hydrogen will be transformed into electricity by an equipment which is called fuel cell, a hydrogen fuel cell to be more precise, because there are other types of fuel cells as well. Then this electricity, which is once again in direct current form, is temporarily stored in a battery, especially to absorb different variations of power along the way. And then from this temporary storage, it will feed the electrical motor on board the train to provide the traction required. I see that I have a first question. Thank you for your question. Is it possible to remove the battery with the hydrogen technology, and is the battery size smaller in this case? Thank you for your question. I'm guessing the smaller refers to the battery solution. To answer your first question, it's hardly possible to remove the battery totally, because fuel cells are equipment which run at a stable rate. They don't like instant variations in their output. So in order to downsize the fuel cell, it's most interesting to have batteries in order to absorb the peak demand in terms of acceleration, or if you are going uphill. The second part of the question, is the battery size smaller in this case? Yes, definitely. You do not need to store all the energy required to fulfill the trip. You need the equivalence of minutes of consumption in the battery and not the whole trip. I have a second question. Do you think that the regulatory aspect could be a limit to store 50 cubic meters at 350 bars? I don't think regulations will prevent us from doing so. There are other applications which will require larger amounts of hydrogen. 50 cubic meters at 350 bars is almost 1 ton of hydrogen on board. And if we look at the space applications, for example, we are already talking about tens of tons of hydrogen. There is regulatory work to be done. Not everything has been established as we speak today, but I don't see a major roadblock to do so. Now that we have looked into different applications of hydrogen, it's time to have a look at the different segments of the railway industry. Railway industry fulfills different types of missions. I mentioned the high-speed trains in my introduction, but there are 3 other main segments in the railway industry. The second one being urban rail, the subways, tramways, etc. The third one being regional trains, and on the 3 first ones we are mostly talking about passenger traffic, and the fourth segment, which will be freight. The share of each segment in different regions and countries vary a lot. Just to give you the 2 extremes, in France it's mostly concentrated on passenger traffic, but if we look at the United States, somewhere around 95% of the railway industry is concentrated on freight. So stakes are different in different regions and countries as well. But if we try to have a look at what would be the most relevant low carbon technology for each of these segments. We can focus on the last two, because on high-speed trains and urban rail, more often than not, the electrification and electricity is available, and I'm not even talking about the technical challenges that batteries and hydrogen fuel cells will pose. Batteries will get definitely too heavy, and the hydrogen fuel cells, as I mentioned, for the high-speed trains, that they will provide us with problems in terms of volume. But the two last applications are potentially interesting both for batteries and hydrogen fuel cells, and I will talk a little bit more in detail in a minute about these. The regional trains are most particularly interesting because we have a more limited mission profiles in terms of size and range, as we will see in a minute. I will speak a little bit less about freight, because the variety that we will have on the mission profiles makes it hard to have one final clear conclusion on that. Just before moving to our conclusion line, I just wanted to speak a little bit about what we did. We created a comprehensive total cost of ownership model for the different technologies, and we assume that each of these technologies will be mature at scale. And we tried simulating different mission profiles with all four technologies. And by calculating the total cost of ownership in terms of money per seat kilometer, we tried to identify what would be theoretically the most cost-effective solution, at least among all four, depending on the different missions that need to be required. We took into account several topics. The first one being the infrastructure cost, which will be amortized over a period of let's say 30 years. The cost impact on the rolling stock, because trains will have different architectures as well. Lifetime of equipment on board will vary as well. And one of the most important topics is actually the fuel cost as well. And we added on top of that other costs which will not vary, the operations, well, the conductor that you have on board which will be the same in each and every technology, the rail infrastructure cost, etc., which will remain the same. And I would just like to speak 30 seconds about the simulation that you see on the screen before moving to the more general results. If we take a pretty light regional train with a typical range of 200 kilometers, 2 trains running on the line, etc. As you can see, our model suggests that hydrogen will not be the most cost effective if we include diesel, but if we take the balance of cost and carbon emissions, we will already have emission reductions of around 80% compared to a diesel solution, with a small cost increase of around 7 to 10%. And it clearly comes out as the most relevant solution in order to reduce emissions. We can go beyond that level of emission reduction by electrification on batteries, but the cost increase, the marginal added value will be much less, and hydrogen seems to be the most relevant solution on this. We conducted the simulations that I mentioned on several different scenarios, and this is what I wanted to present as a conclusion of what we did. Once again, I should announce a few disclaimers before I give you the general conclusions. The simulations that we ran are for a new line. So the line does not exist. So all the capex is included. Those concern all or nothing solutions. So we did not take into account partial electrification or hybrid solutions for the trains, and they do not take into account every single specificity that we could have in the location. And we tried to map based on the range or the autonomy of the train and the average traction power required by the train, which would be the most relevant technical solution for this application. And as you can see, with the limited amount of energy to store on board, the conclusion was that batteries make the most sense. This is the yellow range that you see on the mapping. If the amount of energy is extremely high, so high power over high ranges, electrification becomes the only solution viable as well, most importantly because of the impact we will have on the rolling stock. And there is some place in between for hydrogen, where batteries could not fulfill reasonably well the function, and the electrification will not be cost effective. One parameter which is not taken into account and which is fixed on this graphic and which is of paramount importance is the number of trains that you will have running on the line. The more traffic that you will have, the easier it will get to amortize the cost of electrification over a larger number of trains. And I would like to speak a couple of minutes about every frontier and border that you see. I will start with the one between batteries and hydrogen, which appears somewhere between 100 kilometers and 200 kilometers. This is the trade-off between the mass increase that you will have due to batteries and the higher OPEX cost, especially on the fuel side, that you will have on hydrogen. Hydrogen will be more expensive per kilowatt hour, but storing hydrogen will be more mass effective, if I may call it so, on board. So the impact on the rolling stock will be less. Obviously, the precise location of that frontier will depend on technological progress on both technologies. If the energy density in batteries goes higher, which is the tendency, that the frontier will move to the right, and every single efficiency gain on the hydrogen architecture will move it to the left as well. And before moving on to the next topic, I will try to answer a question. Is it correct that for fuel cells, the hydrogen has to be high quality, free of pollution, and hydrogen as a rest product, for example, chemical industry, cannot be used in fuel cells? That is true. You need more than 99.9% purity in hydrogen, which is not difficult to achieve via electrolysis. The output of electrolyzers is already at more than 99.97, if memory serves me right, purity. Yeah, so it needs to be pure. Do we take into account the lifetime of the different equipment? That's a perfectly valid point as well. And then, and thank you for that question, because I was about to forget that topic. It's actually one of the other main parameters which might change the balance between different technologies. To give you an this element is taken into account, but to give you one of the most important example, it is the lifetime of the fuel cells, which are currently approaching 10,000 hours of lifetime, which will not be enough. But huge progress is being made on those, because we are only at the beginning of high volume fuel cell production. And last question is, which price for H2 was taken into account in the TCO analysis? Which is, once again, a very good question, and thank you for that. The cost of the hydrogen production will vary a lot depending on the source and the location. The hypothesis that we have behind this model is around $5 per kilogram of H2. So not really current rates, but not the most optimistic and ambitious targets which are set either. It is supposed to be an average cost across the globe. So it seems that I've answered every single question. Then I will move on to the second topic, which is the frontier between hydrogen and electrification. Well, electrification is the most cost efficient if we look into the fuel topic, because you will produce electricity and you will consume it directly without any intermediary transformations. And as we saw in the hydrogen architecture, there's a lot of unnecessary transformations going on. Here, once again, the balance is pretty simple. It's a classical CapEx versus OpEx optimization problem. You will need to invest more in the rolling stock in case of hydrogen. Your kilowatt hours will be more expensive, but your infrastructure is pretty limited because you just need 1 or 2 refueling stations at each extremity of your line. But as the amount of hydrogen energy used for each train goes up, the balance shifts towards the electrification, and as you can see, that this is why the higher the range, the lower the power where the switch happens. And the last Sophie's choice that we have between batteries and electrification happens around 50 to 100 kilometers for the higher power applications. And once again, this is mostly about the mass impact of batteries. Here, hydrogen will not even appear as a candidate, especially because of the volume that it requires. Once again, the balance might shift if battery technology is evolving, and we might actually go up to somewhere around 100 kilometers. I promised that I will be speaking a little bit about freight railway. There's one interesting application for battery fuel trains, which are the freight shunters handling freight on over a very short distance, 10 to 15 kilometers, and which are not running all the time. These will be the perfect candidate for battery application. So now that we have seen an overview of what would be the role that hydrogen will need to play in the railway industry, I would like to speak a little bit about the challenges for large-scale hydrogen trains. For those of you who participated in our aviation hydrogen webinar, you probably remember that we had 4 on aviation, and 3 of which still appear on hydrogen. The first one is obviously the operational cost impact. Doing the railway industry in a cleaner way will most probably come at a higher price with hydrogen. But as we saw, the cost impact is relatively limited, and it should be offset either by carbon taxes on diesel transport, which is one way of leveling the cost, or increasing the price for passenger tickets or the cost per ton per kilometer. The technical issues are of much less importance compared to aviation, since hydrogen trains are already running. The major work which remains to be done is to design the real hydrogen train, since the ones which are already running are mostly retrofits of diesel trains, as we will see in a minute. These are adaptations of diesel trains. There is still optimization to be done on these types of trains. And the last topic is that obviously converting diesel trains to hydrogen, especially with the electrolysis source, will require an increase in global electricity production. Fortunately, the diesel railway transport is relatively small compared to the other segments of mobility all across the world, and replacing every single diesel train would only require a 5% increase of current global electricity generation. Once again, for those of you who remember aviation, it was around 35–40%. Just to finish on these key takeaways before moving to the Q&A session, I would like to speak a little bit about the two first challenges that I mentioned. The first one being the cost. Well, we all remember that the aim of moving to hydrogen is to reduce carbon emissions. And it's not all about using hydrogen or not. It's mostly about the way hydrogen is produced. Hydrogen is produced in through two main processes. The historical one, which is called the gray hydrogen. To put it in a nutshell, it's about breaking fossil molecules, separating hydrogen from carbon, emitting the CO2 to the atmosphere, as ironic as it may sound, and keeping the hydrogen, which is somewhere around 96–97% of current production. As you can imagine, well, it's not very eco-friendly, but it's very cost-effective, done at a very large scale in what is called steam methane reforming units. On the other extreme, the new technology which appeared is the production of green hydrogen, so electrolyzing water with renewable energy, very, very low emissions, around 25 grams per kilowatt hour of power produced, so dividing the emissions by something like 15, but pretty much more expensive at $7 per kilogram of H2. Well, the $7 that you see will depend a lot on the cost of kilowatt hour of renewable energy available in the region. But the main cost driver here is that your electrolyzer will not be running all the time. It will only be running when renewable energy is available. And then we have the intermediary solutions of blue hydrogen, which on one side consists of producing gray hydrogen, but capturing the CO2 coming out of the process instead of letting it go to the atmosphere, with potential reduction somewhere between 70 and 80% of what is coming out of the unit, or doing electrolysis with energy which is not necessarily renewable, coming from the grid. And here, once again, the issue is that the electricity mix in different countries have different emission levels. If I take two extreme, in France, we have somewhere around 30 to 50 grams of kilowatt hour per kilowatt hour, depending on the day. Or if we go to China or Germany, it can easily be multiplied by 10. Before moving to the rest of it, the price for H2 of $5 per kilogram, is that the supply of H2 to the HRS only, or also taking into account the HRS CapEx and OpEx? Just to explain a little bit before answering the question, HRS is hydrogen refueling station. So the question is whether or not it includes the dispensing cost as well. The $5 per kilogram is a reasonable target for dispensed hydrogen. It's not only about production. The figures that you see currently on the slides are more or less the state of the art as per today, that they are supposed to go down, especially with full-scale deployment of hydrogen production. And 5 was a target for dispensing. The dispensing cost is a little bit below $1 per kilogram of hydrogen, and then the whole supply chain cost will obviously depend on where the hydrogen is produced. So coming back to what I was saying, it's the cost impact is all about finding the right balance between the emission reduction and cost. As we saw for the different low carbon technologies, including batteries, it's not black and white or gray or green in this case. The additional cost and the emission reduction will go in the same direction, and depending on the electricity source which is available in each location, one of the two shades of blue or green should be chosen. Well, the gray hydrogen is obviously of almost no interest because the emissions will not be reduced in a significant way. But depending in location, and I will give you a few examples saying illustrating a case where each solution will be most interesting. Well, green hydrogen, for example, in countries with abundant renewable electricity, such as Southern Europe or North Africa, will be the way to go. Blue H2 by electrolysis in France, it could be a solution. If you have a large portion of your electricity coming from nuclear sources, so very low emission, it could be interesting. And blue H2 with SMR could be a solution for islands, isolated locations. Singapore comes to mind, where the amount of surface required for deploying renewable energies is a bit complicated, and you do not have enough place to produce a lot of renewable electricity. The grid mix is not that clean, so capturing CO2 out of the existing units makes actually a lot of sense. So the second challenge that we had, and I already spoke about it a little bit, is about the technical maturity. Once again, feasibility is not a huge topic. It already runs. Without trying to minimize the efforts done by the likes of Alstom, it just took a little bit of adaptation of the older Coradia trains to make them run on hydrogen, by removing the diesel power pack and the diesel tank and replacing them with the hydrogen tanks on top of the train, as well as the fuel cells. But this whole architecture could be optimized so that the transmission is done in a more efficient way. The electrical traction motor could be included in the bogies as well directly. So there is a lot of tinkering to be done in order to make it more efficient, as I was saying. So just to summarize the key takeaways and messages before moving to the final Q&A session. Well, hydrogen trains are technically feasible, already running. So on this side, there are no major difficulties. And they have their role to play in lowering carbon emissions of the railway industry, especially with greener hydrogen. So we need new infrastructure for cleaner hydrogen production to reduce the emissions, and that is where the focus should be. The train application has the advantage of having relatively simple infrastructure, as trains are dedicated to a line. In order to have a pilot project, you just need 1 or 2 hydrogen refueling stations on the line, have the right trains, and let them run. If you remember the issue that we had with aviation, well, a plane could fly from everywhere to everywhere, basically. So this would be easier, and the pilot projects will take care of it. The fourth topic is that hydrogen costs will go down. Currently, they are relatively high, both on hydrogen production and on hydrogen trains as well. We are once again still at the prototype phase with not necessarily optimized architectures. So the cost benefits will come quite quickly on these topics as well. And the last important message was that there is one particular application which seems to be the most promising for hydrogen trains, which is the lighter part of regional trains in countries where electrified lines are pretty rare or represent a smaller limit of that country's networks, with ranges somewhere around 100 kilometers to a few hundred kilometers. So that's all for my presentation. I just suggest that we move to the Q&A. Okay, first question is, if hydrogen is not green, would not it be more cost effective to use sustainable fuels in conventional diesel engines? This is a very good question. This is a topic that we mentioned a little bit in our aviation webinar, and it deserves at least a minute or two of speaking. Well, if we are talking about synthetic fuels, we have different categories. The ones which are actually based on hydrogen production and synthesis with CO2, they represent almost no advantage. If hydrogen is gray, then their emissions would be even worse. If the hydrogen is green, the problem is that the cost will probably be even higher than hydrogen. But if you're talking about biofuels from biomass, this is something which can be considered. But to give you an order of magnitude, we will be requiring 20 million tons of these types of fuels just to fuel just to replace fossil fuels for train industry, and agricultural resources might become an issue as well. So it could be a transition solution at a smaller scale, but it's hard to imagine that switch at a very large global level. Okay, could you please elaborate on freight trains? Can H2 be of interest? Well, on freight, as I mentioned, there's already one application which could be of interest. If we have lighter shunters move with limited power and limited range, it could be of interest. For the very long range of application of freight, as it is done in the United States, there could be a potential application, but it requires quite a specific analysis of what the current infrastructure is, because we will not be talking about new lines. It will be mostly about installing refueling stations along the way, and there's a lot of detailed study to be done on what would be the impact in terms of running time and the load. This is something which will require specific studies, case per case. So I don't see any new questions coming in. Thank you everyone for your time. You will see my email address appearing in the chat tab, and if you would like to discuss any further topics regarding hydrogen in the railway industry, please do not hesitate to write a quick email to me. The support of this presentation, as well as the replay, will be sent to you beginning of next week, and feel free to check our LinkedIn page as well for the calendar of the upcoming webinars in the coming weeks. Thank you very much and have a nice day.